Okay, so now let's take a look at our second example. So still, we want to minimize a function on the two-dimensional domain. And here that means we have two decision variables, x1 and x2. Okay, so you may see that the function now looks a little bit more complicated, but still it's a second order function. Alright, so we may still first get our gradient, which is here. So I'm not going to go through the details, but I guess you may just help yourself. And then we are searching for a point that satisfies the fact the gradient is 0, right? So let's first do some analysis to see which point would satisfy the condition for your gradient to be 0. So pretty much you are solve this 2x2 linear system, okay? Gaussian elimination, whatever, you're going to get -2, -1 as the unique point that may make the gradient 0. So this can be done, and later we will show you how the search process eventually converge to this first order point, okay? So in fact, we may show you that this -2, -1 is indeed globally optimal for this particular f function. Now this is possible to be shown, but here we're going to ignore this part because we don't have enough tools to talk about this. We just want to use this example to show you how the numerical derivation, numerical calculation for gradient descent may be done, and also how it converges to a first order point. Let's say we start at 0, 0. Then the gradient may be found by plugging 0, 0 to the gradient function. So we get 2, 0. And then we need to solve for an a. And to solve an a, again, we play the same trick. Here, x0 is 0, 0 minus a times the gradient. So you get -2a and 0. So you plug in this -2a back to your f function. You're going to very quickly see that you obtain this one. Okay? So somehow you want to find a to minimize the function 4a squared minus 4a. So very quickly you may see that this gives you an optimal solution, which is 1/2. In that case, we're going to have our x1, which comes from 0, 0 minus 1/2 times 2, 0, and then it results -1, 0. So that's a very typical iteration. We may do this thing again. So there you may try yourself to see, oh, okay, so you get another gradient vector. And then you move again along the opposite direction. You now need to solve for a again. So you do all the things again, and I'm not going to do this for you now. So we're going to try to minimize 8a squared minus 4a minus 1. And this gives us an optimal a1, which is 1/4. So if that's the case, then again, here what you may do is to find your next solution. So just to remind you that when we want to apply gradient descent in this particular manner, always you need to formulate a sub-problem, which is also a minimization problem. And in that case, you want to find the step size that can minimize your height, minimize the objective function value. So if that's the case, we always get a one-dimensional problem. Even if originally you have n-dimensional, you have n decision variables, okay? But after you try to do this, your initial point must be some values. You subtract a times your gradient, another several values. Somehow the outcome is still a function with a only. So you may just optimize over a, okay? So this problem always is a one-dimensional problem. And for one-dimensional problem, doing the optimization in some cases is still hard. But at least for these quadratic examples, it's not so hard. We know how to do that. whenever your function is quadratic, you take a look at the coefficient. So it has an upward curvature, so that means your first order solution is optimal. So maybe, for example, here, you do one first order derivative. That's how you get a to be 1 over 4. Or you play your high school trick, all right? So that's also something you know how to do it. So anyway, I'm going to delegate the derivation to you, and then let's move to the next page. So the interesting thing is that if you depict the search route that you move from x1 to x0 to x1 to x2, you're going to see that, okay, x0 is here, x1 is here, x2 is here. And if you also depict our gradient f, okay, for gradient f, you actually have two functions, right? And if you depict the fact that the so-called first order condition or the gradient must be 0, if you see that, you're going to see that you get two straight lines. One is here, one is there. So the two straight line is nothing but setting your gradient to 0, okay? That gives you the two straight line. And if you want an intersection, that's here. It's -2, -1. So the thing is that pretty much we know that what our algorithm is doing is to search only one direction once a time. So why do we know that? Because pretty much every time when we are doing the gradient thing, you're going to see that for each of the gradient, here, here, or here, one of the elements must be 0. So that means you either go in this direction, or that direction, or that direction. Also, when you move along one direction, for example here, you obviously would stop at -1, 0. Why is that? Because along this direction, if you consider this as a one-dimensional problem, then for this particular curve, -1, 0 must have the smallest functional value, because this is the point where your first order derivative is 0. Okay? Along the second direction is the same thing. You must stop at -1, -1/2. Why is that? Because along that direction, the blue line, the blue line is always the place for you to have the first order derivative or the gradient 0. And that's the minimum location. Okay? So by knowing all the things, we don't really need to carry the next iteration by using the original formula. We actually may predict that x3 must be on this particular line. So it must be -1.5, -0.5. Also for x4, it must be here. x5 must be here, x6 must be here, x7, x8, Eventually, you will really get to your optimal solution, your desired intersection. So here, I tried to show you some properties of your gradient descent search. So you not only just know how to do the numerical derivations, you also can see that when you do the search, you really stop at the minimum location point or minimum height point. And also, maybe you have also noticed from the previous two examples, when you do gradient descent, you pretty much always go in the right angles, okay? In the previous example, it's something like this, right? They are also right angles. Somehow this is true if you always try to move to the best point you may do when you do gradient descent in each iteration. But of course, that's also something that I'm not going to prove here. So at least you know one thing. For gradient descent, you know the general strategy, you know how to implement it, you know how to go do all the iterations. Then you have one tool that may help you solve or at least generate a solution for nonlinear programs.